This is Dr. Sirisha, working as Associate Professor in Institute of Aeronautical Engineering. Today we are going to discuss about balanced set trees, also known as AVL trees. So, what an AVL tree is? AVL tree is known as a balanced set tree because its balance factor must be either -1, 0 or 1. Or I can say that the balance factor should be 0 or a difference. The difference of the heights of left and right subtree must be, difference must be 1. That is either +1 or -1, not more than that. Or they can be of equal height, right? So such a tree is known as balanced set tree. Have a look at the example which I have given over here. Okay, so 25 acts as the root, right? And this is the left subtree and the right subtree. Left subtree is headed by 20 and the right subtree is headed by 36. So what will be the height of left subtree? 1, 2 and 3. So when we are talking in point of the root, so 3 is the height of the left subtree. Coming to right subtree, 1, 2 and 3. 3 is the height of the right subtree. So the difference will be 0. Right? So the balance factor of the root element 25 is 0. In this way, if you calculate the balance factor of each and every element in the tree, you have to get either 0 or -1 or +1. No other value. If this property prevails, then we call such a tree known as a balanced set tree or an AVL tree. So have a look at another. Let me look at another example. 30, say. So its left subtree length is 1, whereas it doesn't have any right subtree. So its height will be 0. So the balance factor will be 1. So you have to, at each and every step after even insertion or deletion, if you have a look at that, then in that case we call such a tree as an AVL tree. So when a tree is not an AVL tree, it is not following the property, the basic property of an AVL tree. So some of its internal nodes or maybe at times the root node is not having a balance factor within these 3 values. It is having something else, either -2 or +2 or some other value. Then we can rebalance it. We can rebalance it using one of these rotations. So rotation is the process of moving the nodes, either left or right, to balance it, to bring it back to the property of AVL trees, right? So basically we have 2 types of rotations, single rotation and double rotation. In single rotation, left rotation and right rotation, whereas double rotation, left right and right left. So these are the 4 kinds of rotations that we have in our hands. Then which rotation technique which we need to implement, that we are going to see now. It all depends upon the element which got newly introduced into the list or construction of AVL tree, which made the tree get imbalanced. So have a look at this example. So initially the process is of inserting 1, 2 and 3. So our balanced set tree is nothing but a binary set tree, first of all. Basically, I hope you know that, right? What is the property of binary set tree? Binary set tree tells that all the left elements must be less than or equal to the root, whereas the right elements are greater than the root, right? So similarly, let me do the same. Okay, so let me redraw that. When I insert 1 here, let me calculate the balance factor. As it is a single node, its balance factor is going to be 0. No problem with this. Then let me insert 2. As 2 is greater than 1, it is going to come and sit as the right child. Now let's calculate the balance factors. So the height of left subtree is 0, whereas right subtree is 1. So the difference, the balance factor will be -1. Whereas for 2, as it is a leaf node, no left or right child, so its balance factor is 0. Even here, there is no problem, right? So next, let me insert 3 now. As it is greater than 1, it is going to go in the right direction. As it is greater than 2, it is going to sit as the right child of 2. Again, let's calculate the valence factor. So the left length of 1 is 0, as 1 have no left child. Coming to the right, it have 2 children. Yes, its balance factor is -2. Coming to node 2, it doesn't have any left child, but it have a right child. Its balance factor is -1, right? Coming to 3, as it is a leaf node, its balance factor is 0. The story is till now it is okay, but what about -2? It violates the rule. That means node 1 violates the rule. Why node 1 have violated the rule? Because of inserting a new element in the right subtree, as a right child. Do you get my point? When a new node, you can say a new data element or a new node got inserted into the tree as a right element in the right subtree. Now the weight in the right subtree is more. So when the weight at the right subtree is more, how you can balance? Just pull it towards left. Very simple. Pull the head of 1 to the left hand side. When you pull it to the left hand side, when it gets rotate itself 1 step down, 2 is going to become the head or the root. So and 1 becomes the left child of 2, right? So 3 will be as it is, the right child of 2, right? So the story ends here. So now again calculate the balance factors. If you calculate the balance factors of 1 and 3, as they are children, right? They are leaf nodes. As they are leaf nodes, their balance factor will be the 0. Whereas when you calculate the balance factor of 2, its left child is 1 of height and right child is of height 1. The resultant balance factor will be 0. Right? So now you can see that the tree is balanced in nature. Only thing you have to remember is what is the new element which entered the tree, which caused the imbalance, and what is the node which got affected because of this insertion. Okay, so have a look at this example. So I'm going to insert the things in a reverse order. First 3. Its balance factor, as it is the only node, its balance factor will be 0, no problem. Now I want to insert 2. As 2 is less than 3, insert it as the left node. Let's calculate the balance factors. So the left height of 3 is 1, whereas the right is 0, its balance factor is 1. Coming to 2, as it is a leaf node, its balance factor is 0. So there is no violation of our AVL property. Now it's running smoothly. What if I insert 1? 1 is going to come and settle as the left child of 2, as it is less than 2. Let's calculate the balance factors. So the left subtree height of 3 is 2, whereas right is 0, as it doesn't have any right child. Balance factor is 2. Coming to 2, its left child's length is 1 and right is 0, balance factor will be 1. As 1 is a leaf node, its balance factor is 0. Fine. For 2 and 1, the story is okay. But what about the node 3? Its balance factor is 2. It violates the rule of AVL, right? So why this happened? Because on the left hand side, a new element got settled as a left child. Am I right? So in the left hand side, 1 got settled as a left child, right? So the weight in the left side is heavy. the weight in the left hand side is heavy, what to do to balance it? Pull it to the right. So which node got imbalanced? The node 3. So your diagram says the same. Pull 3 towards the right. When you do that, so when you forcefully do that, 3 is going to come as the right child of 2. Have a look at this one. So 3 is going to go as the right child of 2. Now again calculate the balance factors of 1, 2 and 3. As 1 and 3 are leaf nodes, their balance factor will be 0. What about 2? Its left and right children are having a balance factor 0, right? So as their length is heights are also same, even the balance factor of 2 is 0. So now you can see that with the right rotation, a single right rotation, we balance it, the AVL tree, right? So these are the two cases. Remember, if the weight because of a new element being inserted in the left subtree, in a left as a left node, you have to pull it towards right because on the left side weight is more. The vice versa, the same with the right side also. Okay, right. Now have a look at a bit more complex one. Left-right rotation. Why this happens and how this happens. Let's start with the insertion of 3, 1 and 2. So 3. When I insert 3, no problem. As it is the single node, balance factor is 0. When I insert 1, 1 is less than 3, it settles as the left node of. So balance factor of 1 is 0 as it is a leaf node, whereas 3 is 1 minus 0, which is 1. Even now there is no problem. Now what if I want to insert 2? As 2 is less than 3 but greater than 1, it settles as the right child of 1. Now again calculate the balance factors. 2 is a leaf node, 0. 1, its left child 0, right child 1. So minus 1 is the balance factor, no problem. Coming to 3, its left side length is 2, whereas right is 0. So the height of the left subtree is 2, whereas right is 0. So balance factor is 2. Now there goes something wrong, right? So 3 got imbalanced. Why 3 got imbalanced is the point. Because of which node? Because of 2. Because of 2, 3 got imbalanced. Where 2 was inserted in the left subtree of 3 as a right element, it was inserted. Once again, I'll tell you, listen to me carefully. So in the left subtree, as a right element, it was inserted. Please keep that in mind, right? So in that case, we are going to do LR rotation, nothing but left-right rotation. So left of what and right of what is the primary question that you are going to get. Let me elaborate the same. As this is left and right rotation, I am going to break it into 2 halves. First is left rotation, next is right rotation. Okay, then coming to the left rotation. For which element I am going to do the left rotation? Have a look at the node which is the head of the left subtree of the affected node. What is the node which is affected? 3 is the one which is affected. Which element is the head of the left subtree? 1, right? Rotate it towards left. Remember, the head or the subroot of the left subtree of the affected node, you have to move it towards left. When I pull 1 towards left, 2 is going to raise its head and 1 is going to settle as the left of 2, right? So now let's go for the second step, which is right rotation. In case of right rotation, do perform that operation on the node which got affected, which is 3. Pull it towards right. When you pull it towards right, 2 is going to go top and 3 is going to settle as the right subnode, right subtree of 2. Now check the balance factors of 1, 2 and 3. So it will not violate the rules. Remember, you have to take the decision of left rotation, right rotation or left right rotation depending upon the element which you are going to insert and the affected node. Okay, first of all, get the relation between these two, the newly inserted and the affected one. The last rotation technique, right, left rotation. Let's have a look at this one. Initially, I'm going to insert 1. As this is the only node, no violation of balance factor. Next, 3. As 3 is greater than 1, right node of 1. So balance factors. 3 is a leaf, so 0. For 1, it is 0 minus 1, which is minus 1. And even now, there is no problem. Okay, the problem will raise when we insert 2. Okay, so where 2 is going to sit? As 2 is greater than 1, it will go to the right side. As it is less than 3, it will go to the left side. So 2 is going to sit over here. As 2 is a leaf node, its balance factor will be 0. Coming to 3, its left node is 1. Minus right is 0, which is 1. No problem. Coming to 1, its left subtree height is 0. Right is 2. Minus 2 is its balance factor. Now the problem raises. 1 got violated with its balance factor. Because of what? As I told you, 2 points you need to keep in mind. The node which got affected and the node which was newly inserted. Because of the newly inserted one, it got affected, right? So let's check these two. Affected one is node 1 and the newly inserted is 2. Then let's build a relation between these two. Where 2 was inserted? In the right subtree as the left child. Think in the point of view of 1. 1 is thinking that my balance got violated. My AVL property is violated because of 2. Where is 2? In the right subtree of mine, it is sitting as a left child, right? So in that direction, in that way, if you think, it will be quite easy for you guys. Okay, so now we have to perform right-left rotation because in the right subtree, the new node settled as a left child, right? So let's divide the rotations into 2 halves. First is right rotation and then left rotation. Let's see how I'm going to do that now. Okay, then right rotation of what? So right rotation of the head of right subtree of the affected one. What is the node which you got affected? 1, right? Then who is the head of the right subtree? 3. Rotate it towards right. If I pull 3 towards right, 2 is going to raise its head and 3 is going to settle as the right child of 2. Guys, you have to remember always, even at the intermediate rotations also, the BST property, binary search property, should never ever be violated. Okay, so have a look at this one. 1, 2 and 3. Right? Now left rotation. First rotation is over. Left rotation. Left rotation of the affected node. What is the node which got affected? 1. Pull it towards left. When you pull it towards left, 2 is going to raise its head and 1 is going to settle as left node of 2. So now check the balance factors of this obtained result. So you'll get a balanced tree. I have given the results out there. Right? So remember, we have 4 types of rotations to balance an imbalanced binary search tree. How many? Look at the node which got affected and the node which is newly inserted because and build a relation between these two where the new node got settled. So based upon that, take an appropriate rotation decision. Okay. So I can explain you with this an example. I've taken a simple example of numbers 1 to 12. I want to construct a AVL tree with that. So 1, as I have that inserted or started the AVL tree, it is the only node, its balance factor will be obviously 0. Now I want to insert 2. As 2 is greater than 1, it is going to settle as the right node, right? So again calculate the balance factor. 1 and 2. 1 balance factor is -1, 2's balance factor is 0. Violation is not there. Now insert 3. As 3 is greater than 1 and 2, it will settle as the right child of 2. So the balance factor of 3 is okay as it is a leaf node, it will be 0. 2 is -1 and 1 is -2. I have pinpointed 1 as red. It is the node which got violated. Guys, have a look at this one. What happened? In the right subtree, an element got inside the AVL tree as a right child. Means what? The weight in the right hand side is heavy. If the right hand side is heavy, pull one towards left. Very simple solution, right? So if you pull that one, then 2 is going to raise and 1 is going to settle as the left child of 2. Again calculate the balance factor, you will get all zeros, right? Now my task is to insert 4. As 4 is greater than 2 and 3, it is going to settle as the right child of 3. Calculate the balance factors. Now the story is fine. Now insert 5. As 5 is greater than 2, 3 and 4, it is going to settle as the right child of 4. Again calculate the balance factors. You can see that the node 3 and 2 lost their balance. Their balance factors are -2. This is the case where you need to think properly, take a decision properly. What is the node which is newly inserted? 5. Okay. Now have a look at the node or search for the node which is nearer to 5 and which got imbalanced. So if you travel towards the root, you will find 3 as the first node which got imbalanced because of 5. So try to give justice to 3. So in point of view of 3, what happened? A new node in the right subtree entered as a right node. So that is the problem. So the right hand side of 3 is very heavy. So pull 3 towards left. That is the first one you are going to do. Left rotation. Do it. When you left rotate it, 4 is going to raise and 3 is going to settle as the left subtree and 5 will be as usual, the right subtree of 4. Calculate the balance factor. If you calculate the balance factor, you will find that even the problem of 2 got rectified. Even the problem of 2, which was -2 earlier, is -1. It came to the zone of the balance factors of an AVL tree. Correct? So always think or consider the node which is being newly inserted and the nearest node which got affected by it. Right? So let's continue our process. Insertion of 6. When I inserted 6, which got settled as the right child of 5, node 2, that is the root node, got imbalanced. Now let's think in the point of view of 2. Why it lost its balance? Because of some node in the right subtree got settled in the right side. Right? So what you have to do? Very simple. hold 2 and pull it towards left. Right hand side bhari hai, left side khincho. And if you do that, 4 is going to rise its head. As 4 has raised its head, the 2 and 1 are left to it, that will be okay. And 5 and 6 are right to 4, that will be okay. 3, which was previously in the right side of 2, now it will be on the right side of 2. Now have a look. This is an intermediate AVL tree which we have constructed for numbers 1 to 6. Still, it is a BST. Guys, kindly remember this hierarchy. Binary tree. So if you put a constraint on it saying that left elements will be less than or equal to the root, whereas right elements are greater than the root, you will get BSTs, binary set trees. And if you put a constraint saying that the balance factor must be -1, 0, or 1, that is the difference of heights of left and right subtree of every node must be either -1, 0, or 1, then it is known as an AVL tree. What do you mean by this? Every AVL tree is a BST as well as a binary tree. Every BST is a binary tree. So, an AVL tree will have the property of BST and it should not lose its charm at any point of time, at any insertion or deletion. Okay, let's continue with our process. Insertion of 7. When I inserted 7, 5 lost its balance. So, as it is because of right element, I'm going to pull 5 towards left. When I do the same, 6 is going to rise and 5 is going to settle as the left child of 6. Calculate the balance factors. Now it's fine. Now insert 8. No problem. Insert 9. 3 nodes continuously got violated. Come on. From 7 to 6 to 4. Right? So, have a look at this one. What is the new element which got inserted? 9. Because of 9, what is the nearest node which got affected? 7. In point of view of 7, why this happened? Because a new element in its right subtree got inserted as a right node. Right? So what is the solution? Full 7 towards left rotation. Right? So when you pull it, 8 is going to rise and 7 is going to settle as the left child of 8. Right? So now insertion of 10. When you insert 10, 6 gets imbalanced. Pull it towards left. You are going to get this. And now insert 11. The root 4 got violated. So have a look at this one. 4 got violated and even 9 got violated. And judge between these two. 11 is the newly inserted one and the nearest one which got affected is 9 because of right element. So rotate towards left. So this is the final one. You rotated 9, even 4 got balanced. Right? This is an indirect effect. This is how we are going to perform AVL rotations. Okay, so to balance a binary tree, binary set tree, more precisely if you see. Okay, so if you insert 12, the root node got imbalanced. All the remaining nodes are happy, only the root got imbalanced. Have a look at that one. So if you pull 4 towards left, 8 is going to become top. So whatever the left of 8 is there will become the right of 4. Have a look at this one. As I said, whatever the left of 8 was will become the right of 4. Again, calculate the balance factors. You can see it is balanced. So this is a AVL tree which was constructed for numbers 1 to 2. As you can even take random values or try to do it in the reverse way. Start constructing your AVL tree for numbers 12 to 1 in the reverse order. Do it. Okay. So let's see the applications of AVL tree. So wherever the cases of insertions or deletions are very less frequent, a stable database I'm talking about, and short search. If you need many times the searching operations, you frequently go for search operations, then we can use AVL trees because they're height balanced, right? So that is a basic advantage. The advantage and the disadvantage are the same as the curse and the bool, right? And the curse with AVL trees is insertion and deletion. If you insert an element, if the balance get loose, you have to rotate the tree, which takes huge amount of time if the database is a heavy database, right? The same story with deletion. If you delete an element and it violates the rule of AVL, you need to rotate the things, rotate the nodes, which again needs a huge amount of time, right? So, but even to construct an AVL tree in the first hand itself, you have to perform loads of rotations, which is highly time consuming. That is the basic drawback of an AVL tree. To overcome that, we have red black trees and many things are there. But it is highly efficient if you have a stable database and you only search for elements. If you only search for elements, then AVL tree is the best data structure which gives the best results. I hope you understood this session on AVL trees. I'll come up with the new sessions with new topics. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.